Hello everyone, welcome to TC online course Statistics for Machine Learning. So in this module we are going to start with the basics of statistics for machine learning. Before we directly jump into machine learning algorithms, we need to understand one important thing. Data is never perfectly fixed or certain. There is always some randomness, variation and uncertainty. So today in this short session we will understand the fundamentals of probability and statistics and why they are very important for machine learning. By end of this lesson, you will get a clear idea about how probability concepts are used in machine learning. Why statistics matters in machine learning. Now many people think machine learning is only about coding models. But actually machine learning is about learning patterns from the data. And the real world data is always messy. That means it contains noisy, missing values and variations. So statistics help us to understand the data properly. For example, when a model gives a wrong prediction, statistics help us answer why the error happened, how confident the model is, and how we can improve it. So statistics plays a basic foundation for machine learning. Core machine learning concepts built on probability. Now machine learning is deeply connected with the probability. Whenever we train a model, we are assuming that the data is coming from some random process. Probability helps us answer questions like how likely is this output? What is the best model for the data? How uncertain is the prediction? So concepts like likelihood, inference and confidence are all coming from probability theory. So what is random variable? Now let us understand one basic concept called random variable. It is simply a numerical value whose outcome depends on chance. For example, rolling a dice, rainfall amount in a day, marks scored in an exam. In machine learning also, we treat many things as random variables, like features such as temperature or soil moisture and labels such as spam or not spam. So random variables are everywhere in machine learning. Probability distributions. Now, random values follow something called a probability distribution. A distribution tells us how the values are spread. Some common distribution used in machine learning are Bernoulli distribution for yes or no outcomes, binomial distribution for number of successes or number of failures, Gaussian distribution for continuous natural data. Distribution helps model understand the behavior of data instead of just mentioning it. You can see the various example for all the different types of distribution for uniform dice roll outcomes, for binomial coin tosses, for normal distribution heights of the students, and for Poisson distribution number of arrivals in a minute. So example is given below that for uniform distribution P of x is equal to equal probability. That means a random integer between 1.5 meter to 1.8 meter. So since we are taking the data set of students height in a particular class. For binomial, it can be represented as number of students with 1.6 meter or 1.7 meter height. For normal distribution, most students around 1.65 meter height. For Poisson, few students are taller than 1.8 meter. Now key summary statistics. Now to describe data quickly, we use summary measures. The most important ones are mean, which is the average value, variance, which tells how values vary, standard deviation, which shows typical spread from the mean. So these are very useful in machine learning for tasks like feature scaling, normalization and outlier detection. So these simple statistical measures play a big role in model performance. Now one very powerful concept is conditional probability. Conditional probability means probability of one event happening given another event has already happened. Say for example, probability of diseases given symptoms, probability of spam given certain words. Then we have Bayes' rule, which help us update our belief based on evidence. The formula for Bayes' rule is P of A by B, which is equal to P of B by A into P of A divided by P of B. This is the foundation for many machine learning algorithms like naive Bayes classifier and Bayesian networks. So Bayes' rule is extremely important in machine learning. From probability to machine learning models. Now let us connect the probability directly to machine learning models. Many models are trained using probability principles. For example, maximum likelihood estimation, minimizing negative log likelihood. Logistic regression outputs probability values. Neural network model also uncertainty in prediction. Even loss functions are based on probability assumptions. So machine learning is not separate from statistics. It is actually built on statistical foundation. In the slide, we are understanding maximum likelihood estimation, also called as MLE, and how it is related to minimizing negative log likelihood. First, look at the left side of the diagram. We have a bell-shaped probability distribution curve. This curve represents the distribution of students' height in a class. Most students will have heights around 1.6 to 1.7 meters, so the curve is highest in the center. Very tall students like above 1.8 meters are rare, so those values fall in the low probability region. Now, the colored dots on the curve represent actual observed student height data points. The idea of likelihood is how well does our chosen probability model explain these observed values. Maximum likelihood estimation means we choose the model parameters such as the mean so that the observed data becomes most probable. Now, instead of maximizing likelihood directly, machine learning algorithms usually minimize a loss function. So we use something called negative log likelihood. The formula for negative log likelihood is ln is equal to minus summation of log p of xi. This means we take the log of probabilities for each data point, sum them, and then apply a negative sign. Log is used because multiplying probabilities becomes very small, and log converts the product into a sum. The negative sign is used because optimization algorithms minimize loss. Now look at the right side of the diagram. We have a U-shaped loss curve. The lowest point of this curve corresponds to the best parameter value. The minimum point is labeled as MLE. So we can conclude maximizing likelihood is equivalent to minimizing negative log likelihood. This is the foundation behind many machine learning models like logistic regression and probability classifiers. So let us quickly summarize what we learned today. Statistics helps machine learning deal with uncertainty. Random variables represents real world features. Distributions describe how data behaves. Bayes rule helps in reasoning with evidence. ML is often used for probability optimization. In the next module, we will go deeper into sampling, estimation, hypothesis testing, and statistical inference for machine learning. Thank you everyone, and let us continue in the next session. Thank you all for watching. We will meet you in the next session.